in this chapter, we're going to talk about the concept of solutions. We've talked about them previously in general chemistry. We had a section on solutions in 1211, but in this chapter, we're going to do more with it. So we're basically going to take what we did in the solution chapter in our first semester, and we're going to expand on it in a number of ways. But first, we need to review a few things from that chapter to make sure we're okay with them still. So first, what is a solution? So as a reminder, solutions, and so this is back from the very beginning, so it's been a while, I know, I don't need the word more, are homogeneous mixtures. So that's going to mean that they're going to be the same throughout, and specifically, we also need to remember that a mixture contains two or more substances. So it's not just one thing. It's got to be multiple things, multiple different substances, compounds, elements in some form, contain two or more substances. And it has to be homogeneous. That's where it's the same throughout our system. So, the parts of a solution. So solutions, what are the parts? We have, first, we have the solute. And then two, we have the solvent. In general, the way we're going to talk about this is the solute is the minor component. And the solvent is the major component, where the solute is dissolved in the solvent. So for example, if we have a beaker of water and we add some salt, so like table salt, what we get is water with some salt in it. And the salt isn't visible clearly. If you put a little bit of salt in it, I just can't draw salt small enough I was just trying to represent it's still there. But as long as it's mixed together, we're going to end up with a solution where the salt particles are the solute, they're the minor component, they are dissolved in the water, which is the solvent. Now, it's also important to remember from the last chapter that likes dissolve likes. So that's talking about how, for example, a polar solvent like water is going to be able to dissolve polar or ionic compounds, whereas a nonpolar solvent is going to be able to dissolve nonpolar components. So those are just some terms. I also want to point out that in 1211, we dealt entirely with solids being dissolved inside liquids. Those were our most common solutions, and they are the ones we're probably going to use the most in this class. But there are other examples. For example, a gas can be dissolved in a gas. For example, the air I'm breathing right now is a solution. It's mostly oxygen and nitrogen. Now, in the case of some gas solutions, sometimes it's not always obvious what's solute, what's solvent, because it's not like one is clearly more than the other. So I'm not going to stress identifying, oh, that gas is the solute versus the solvent, in many cases with gas-gas mixtures, unless it's very clearly obvious. Now, in the case of liquid solvents, we can have solids. You can also dissolve liquids inside other liquids, or even gases inside liquids. For example, soda that you have in like a soda bottle, like if you had a Coke or something, there's gas dissolved in that liquid. That's a solution. And then finally, you can actually have solid-solid solutions as well. For example, alloys. Like if you've got brass, that's copper and zinc together as a solution. That you can't clearly distinguish the copper from the zinc, it all just appears to be brass. So that's what makes it a solution. It is homogeneous throughout. And it's not that there's like a chemical bond, there's not an intramolecular bond between the copper and zinc atoms. It's just relying on intermolecular forces and the fact that these are spread out throughout. Now, another term we're going to use a lot is we're going to use the word solubility to describe how well one thing dissolves in another. So for an example, salt is soluble in water. And I specifically mean table salt here. So salt can mean lots of different things, but we're talking about table salt here. On the other hand, oil is not soluble in water. That's the like dissolves like situation. So the term we're going to use will be soluble, means something can dissolve in something else, or we'll use the term insoluble to mean something can't dissolve in something else. Now, a question we want to know is, why do some things dissolve and some things not? And there is the like dissolves like situation. That can answer some questions, but it's not a perfect answer and doesn't deal with everything. So in general, we have two concepts that together are going to describe this. So why are things soluble? One is going to be what we call nature's tendency towards mixing, which we'll talk about a bit in a minute. So in general, things would prefer to be mixed than not mixed if everything else was equal. Like if there's no particular reason to want to be separated, two substances aren't going to want to be. There needs to be some value, some positive towards that. And then intermolecular forces are going to contribute. So what allows for the best intermolecular forces? Interactions. Those are the two reasons. So I want to start by talking about nature's tendencies towards mixing, what I mean by that. And so our textbook uses the word entropy to talk about this. I'm going to be the first person to say that I don't think we're going to get through a complete great definition of entropy in this chapter. We're going to discuss it again when we get to thermodynamics. So I'm going to do my best with it. But do understand that I think you may have heard a term like entropy represents disorder. And you'll see like a picture of a messy room. I know I see this one in high school or middle school sometimes. And it's not quite accurate for what's happening. That a messy room is not necessarily high entropy and a clean room is, a messy room is not low entropy and a clean room is high entropy or anything like that. So that's not a great way to go with it. So let's talk about a system where this comes up first. So let's imagine we have a box. Let's pretend it's 3D. I can't draw. We've got a panel separating two sides. And on one side, I've got some helium gas. On the other side, I have some neon gas. And let's say there's more than one. I can't draw a lot. We'll draw some more. And it's not that one helium and one neon is bigger. It's just I can't draw it very well. Or to make it more visible, we're going to make two different shapes. Helium's going to be a circle. Neon's going to be a square. No, neon is not actually square. This is just for our pictures. Now, if I were to remove that barrier, what happens is the circles and the squares spread out. And to some extent, this probably makes some intuitive sense. We would be really confused if the squares all stood on one side. Imagine if you went into rooms and the problem was, man, all that darn oxygen. Oh, wait, did I block off part of my picture? I did. No, I didn't. I'm good. All that darn oxygen, it's in that person's seat. I want to sit by the oxygen doctor, Leslie, because I want to be able to breathe. I don't want to have to run down to get new oxygen. I just want to sit where all the oxygen's at. Can I do that? Clearly, we don't fight over our oxygen seats. I'd like to sit where the oxygen is, too. No. The gas spreads out. So this idea is related to something. I'm going to mention a term that we're going to talk about a lot more in future chapters. You don't have to stress about it too much right now. I'm just going to mention it here because I feel like it does a disservice not to mention it all. Is we use this term called microstates. What this means, and we'll do way more detail later, is that when you take a system, how many different ways can you arrange it in that particular order? So for example, all the squares being on the right side and all the circles being on the left side. Assuming there aren't different positions they can move there, there's only one way to do that. But if I want half the squares on one side and half the circles on the other side, there are multiple possible microstates that do that. Because in this picture, for example, we basically exchanged this circle and square that I'm circling here, got exchanged, and then, let's see, and like this square and this circle got exchanged, basically. But we could do different exchanges and still get two on the right and two on the left. We could have changed a different square over. But if you want exactly 4 on the right and exactly 4 on the left, well, then we can't do those exchanges across the middle. So there are fewer arrangements that allow for the arrangement of everything on the right and everything on the left, whereas everything mixed together like this allows for multiple possible arrangements. Those having more arrangements means that the energy is spread out across more possible microstates, which means it's a higher entropy setup, which is favored. We generally shift towards systems of higher entropy, and the universe overall always goes towards higher entropy. Now you can still get things of lower entropy. You can separate the box to the right and left by putting energy into the system. Somehow doing some type of separation technique, it's possible. But that's only true locally. Globally, not just globally, universe-wise, the entire universe, entropy always goes up. We have not found a way to break that rule. It's one of the problems that eventually, if nothing else, will cause the universe to quit existing. Not existing, but not existing in a way that means much to us, because eventually all the energy in the universe gets spread out evenly, and then you can't do a whole lot. We rely on these energy differentials to do useful things. Thankfully, it will be long after us and any of our children are gone if that ends up being an issue, because that takes a much longer time scale than anything we're dealing with. But we're always going towards higher entropy. And when we have solutions, if the components are able to mix, that creates a higher entropy system. I am okay if at this point the only thing you can tell me is, Dr. Leslie, I know that mixing means that there's higher entropy and that's favored. That's okay for now. We will do entropy again when we get to thermodynamics, so we're going to try to give a better explanation there. I will still admit that, at least from my perspective, I don't think it gets perfect yet, but it takes a while, because entropy is a concept that can feel kind of fuzzy for a while. And if you find another person that explains it in a way you like better, go check them out. I'm good with that. But at least for me, I find it's really hard to teach in general chemistry, although I'm going to do my best to make it make a little more sense. So this was step 1. Things like to mix. Now, step 2. If our intermolecular forces are favored, then that'll help us mix. So for example, in our sodium chloride example, I'm not going to draw. So we've got the water, and we've tried to add some sodium chloride. Does it dissolve? Well, if it dissolves, we'll end up with Na plus and Cl minus. Well, that allows for ion dipole forces. So now the oxygen end of the water can get close to the sodium, whereas the hydrogens of the water can get close to chlorines. And I'm not as good a drawer. I'm sure you can find a better version in your textbook or through Google, where you draw a whole bunch surrounding them, not just 2. But the general idea is that allows for a favorable intermolecular forces interaction. But it has disrupted some intermolecular forces as well. Every water that's attracted to that sodium or chloride is no longer attracted to a water molecule instead. So there is a give and take. Having said this, ion dipole forces in this case are going to be strong enough that it is favorable for the water to dissolve in there. But this will not be true in all cases. Now, let me close out of this for a second. I have a figure I really like, but I didn't copy it over. This is one that I found a number of years ago, and I like this explanation. So this is what's actually going to go down that tells us, are we going to get mixing or not? We compare some things. So if we try to mix something, 2 things have to happen. Well, 3 things. The solute and solvent have to break apart in some places because they're basically making holes. The solvent adds some holes that the solute's going to come into. That shifting has broken up some intermolecular forces between the solvent molecules. And the solute molecules have to separate from each other, so they're not getting intermolecular forces interactions with each other. But then when you mix them together, well, now they're in between in those holes, and now they're interacting with each other, and that's favorable. So these first 2 steps cost energy. You're going to put energy in to separate these. The mixing itself, once they're separated, releases energy. And so the overall enthalpy change for the solution is if you add these 3 steps together. Because, yeah. So, what does that help us with? How do we think about that then? Well, then when we deal with solutions... didn't mean to bring that. Come back, go, there we go. Sorry, I'm trying to bring something up on my screen, not on your screen. There we go. I think my giant duck showed up on my screen for a second. I really like the giant duck that gets pulled, the rubber duck that gets pulled by a tugboat. I want to go see it someday. I don't know where it is. I just know it exists now, and it's bigger than a boat, and that just makes me happy inside. So, okay, unrelated, sorry. So, what does this mean? What do we do with it? Well, solutions can be either, when we could combine them, you may remember from 1211, we sometimes get exothermic reactions, where it's a heat release. Sometimes we get endothermic ones. And it's related to that solute and solvent and mixing stuff. So we start at some point here. This is initial. Our initial state, which is where the solute and solvent are friends with each other and they're all attached as much as possible. Then we're going to add some energy in to break up the solute. And that'll get to one step where the solute's broken up. Then you add some more energy, delta H solvent, that breaks up the solvent. So that's going to cost energy. But then you're going to mix, so this is all separated once you get there. Then you mix them together. And we get down here to the bottom, and we get mixed. And that's going to go down based on how much energy gets released by the mixing. If this difference here is negative if the mixing is below the initial. This means that delta H solution is negative, so less than 0. So we release energy. This was like in 1211 when you mix the solid and the water and it dissolves and it heats up the solution because it's releasing energy to it. And that releasing of energy means that it is exothermic. We can also get an endothermic case though. So in the endothermic case, and I'm going to make my head disappear so I don't accidentally right underneath it. So we'll start at an initial case. We're going to add some energy, delta H solute. We're going to add some more energy, delta H solvent. No, it does not matter the order as you write this. Remember, we're treating this is a state function like we talked about in 1211, which means we're not thinking of it as this happens explicitly, like, oh, we took it and we separated each solute molecule first, and then each solvent molecule, and then we mixed them together. That's not what's really happening. Instead, these are individual steps that we can talk about because we can measure how much energy would be involved with those. The real case is we're going to try to combine these together, and if this is favorable, it's going to do some type of moving around, but it's not going to explicitly, like, oh, we must separate first completely one, then completely the other, and then put them inside each other. That's not what's happening. But remember, we can take any set of steps to get to our final answer with a state function. So these are things that we can most easily talk about. Is, oh, how much energy would it take to separate it? How much energy would be released when we mix it? So here, let's say we mix it, but this one, it doesn't release as much energy. So that's the mixed state. And so now there's a difference here. And here delta H is greater than 0, which means it absorbs energy. To do this, it's going to have to get some from the outside surroundings, which means it's going to be endothermic. So these are the two different types of solutions we work with. Now, well, this video is already 17 minutes. There's just one more topic, so it's not worth trying to make a separate video for. So let's talk about the last concept, which is the solubility limit. So what this means is that when you're dissolving stuff, it can't dissolve forever. So in 1211, we just said things are soluble, things aren't. But you know, at least from practical experience, if I put enough salt in a pot of water, eventually the salt stops dissolving. So I can't just do it forever. So when we get to a saturated case, what that means is we've maxed out the limit. We have as much dissolved as possible. And I didn't need to use the word we here. Sorry, that. So as much solute is dissolved as is possible. The other case would be unsaturated, which is going to be when more solute could still dissolve. I still dissolve. These are the two most common cases. And then you will sometimes get solutions that are something called supersaturated, which means you've done some manipulating so that more solute is dissolved than can be stably dissolved. So there are some ways to get solutions where temporarily they've got more dissolved in them than should be. The most common example would be making something that's really, really saturated, has a whole lot of solid in it, and then cooling it down, but doing so in such a way where we don't disturb it, where it ends up being supersaturated. Because as we change the temperature, a lot of solutions can't dissolve as much. But then if we cause any kind of disruption, suddenly, poof, a whole bunch of stuff comes out of solution because there's way more dissolved than should be able to fit there. Now, one last thing. I'll discard the ink. That's fine. I did not. Where is my thing? Sorry about that. I was just trying to paste a picture. There we go. And I don't think there was anything interesting in my file thing. I think it was just a collection of all the videos I've made recently. It was not all that interesting, so you didn't miss much. Okay. So this graph is an example of how we will represent this. So this is a picture representation. So what it's showing you is at a particular temperature, a certain number of grams of solute can dissolve in 100 grams of water. So for example, let's take KCl. If you were at 50 degrees here, and you were to go over, at 50 degrees, it can dissolve around 42 or 43 grams per 100 grams. If you were to increase the temperature, the amount would go up. That's true in most cases, but notice it's not always. So sodium sulfate's the example in this picture. It actually gets less soluble as you increase in temperature. That is unusual, but not impossible. And from this, we can tell things like, for example, let's say I have an 80-degree solution of KNO3 and I dissolve 70 grams in there. That's fine. So 80 degrees up at 70 grams is this point here. That's KNO3. It can easily dissolve there. Now let's say I start dropping the temperature. Well, it's fine until I get to about 43 degrees or so. At 43 degrees, it would be saturated. If I try to go past that, it's likely to come out of solution. Or, if I'm very careful, it may temporarily be supersaturated before it comes out of solution and instead becomes saturated. So, for example, let's say I kept reducing the temperature to 30 degrees. Now, eventually, what would I expect the amount of material to be dissolved? I would not expect it to be 70 grams anymore. Eventually, when the rest crashes out of solution, it's going to go down to around 43 grams. The other 27 grams are going to come out of solution and probably land on the bottom of my container in some way. However the material I'm working with works with that. So that's what happens. Now you'll notice not all substances dissolve the same amount either. So for a solute, it depends on the temperature how much is actually able to be dissolved. So that will be relevant and let us know how much we can get. And I remembered I have to do one last thing so that you can do problems I assigned in this area. So this video will be a tiny bit longer instead of doing two separate ones. That's okay. We have one last concept I almost forgot to show for today. I was thinking of doing it next week, but I went ahead and did it in this chapter, or this last class. Henry's law. Henry's law is that the solubility of a gas in a liquid is equal to something called the Henry's law constant times the pressure of the gas. So, for example, CO2 dissolved in water is almost always the most common example of this. You can put CO2 in water, you get carbonation. Now, if you have a soda and you compare one that's been in the fridge versus one that's been out on the countertop, the one on the countertop will lose a lot of the CO2 in it. That's because not as much CO2 can dissolve at higher temperatures. This is one of those cases where I get to use the word all that I almost never get to say. So all gases, at least everyone I've ever heard of and know of in existence in my textbook agrees. So if there's some other gas somewhere, maybe it's not true. But every gas you're going to be asked about in this class, and everyone that I know of, all gases, the solubility of the gas decreases as the temperature increases. So another thing to note is these things, kH, you can find them in your textbook. These are going to be in units often of molar per atmosphere. So the idea is when we're preparing a solution and we're trying to dissolve some gas in it, there's going to be gas above it at some type of pressure. As you increase the pressure, there are more molecules hitting the surface of your substance, so it's easier for more to get dissolved in there. We're looking at it because what's really happening is we're getting to dynamic equilibrium, like we talked about last chapter. More collisions means more chances for it to be recaptured by the solution, so higher pressures means more can be dissolved. So what we have to do is use our values. So let's take a fairly straightforward problem. Let's say that we want to know if, let's say, I want my solution to have a concentration of 0.10 molar CO2. I want that much dissolved into my soda that I have. I've got it at 25 degrees Celsius. I have to mention this because technically these values are set for a particular temperature. Then if I go and look up in a table in my text, I can find that the Henry's law constant for CO2 is 3.4 times 10 to the negative 2 molar per atmosphere. And the question is, what gas pressure do I need to do this at to be able to make this work? So what gas pressure is needed? So the way we set up this problem is we have solubility of gas equals our Henry's law constant times the pressure of the gas. Well, I want to solve for P gas, so I'm going to take solubility of gas divided by my Henry's law constant is equal to the pressure that I'm going to need. So my solubility is 0.10 molar. My Henry's law constant is 3.4 times 10 to the negative 2 molar per atmospheres. So our molarities will cancel. And then I want to know what pressure this is going to give me. So when we do that, we're going to get that my gas pressure is going to need to be 2.94 atmospheres. Did I cover that up with I am sorry about that. I'll get just that eventually. There we go. Now you can see. the gas pressure we need is going to be 2.94 atmospheres to be able to get our CO2 to dissolve into our gas or into our liquid at a rate of 0.10 molar. So if we increase the pressure, we can get a higher concentration, and if we decrease the pressure, the concentration would go down. So we can adjust it like that. You can also be given a pressure. Let's say you prepare it at a specific pressure, like 1 atmosphere. Then you can calculate, well, how much would dissolve? That's S gas. Or if you weren't sure the Henry's law constant, you could do a test where, oh, this is exactly how much dissolved. This is the pressure. Solve for KH. This is just a case of you've got an equation with 2 variables and a constant. You know one variable, the constant, you can solve for the other. Or if you know both variables and a measurement, you can use that to find what the constant is for that particular substance. So with that, that ends the initial parts of our discussions of solutions. What we'll be moving on to from here in the future videos is we're going to look at a lot of different units of measurement for solutions. So in 1211, we just dealt with molarity, which came up here, moles per liter. But this is not the only way to measure how much is in a solution, and that's what you'll see in our next video.